Welcome back to G Fun Facts Online. Today we are going to talk about the single most expensive problem in the history of electricity. It is not how we generate power, but how we survive time. We have all heard the oldest cliché in renewable energy, which is that the wind doesn't always blow, and the sun doesn't always shine. It sounds simple, but this intermittency is the barrier between us and a carbon-zero future. We have successfully conquered the cost of generation. Solar panels and wind turbines are now the cheapest sources of electricity in history. But we have failed to conquer time. We cannot effectively store that cheap energy for the calm, dark hours known in the industry as the Dunkelflaut, the dark wind lull. That is where our story begins today. We are looking at the race to solve this problem, specifically focusing on a technology that has been stuck in a scientific trap for 50 years. This is the story of the hydrogen-bromine flow battery, the bromine trap, and the geopolitical chess game that might kill it or save it. To understand why we are even looking at weird chemistry like bromine, we have to look at the reigning monarch of energy storage, the lithium-ion battery. Lithium is amazing. It powers your phone, your laptop, and your electric car. But lithium has a personality type. It is a sprinter. It is brilliant for quick bursts of power. But if you try to stretch a lithium battery to cover a 12-hour shift, or a 24-hour shift, or a 100-hour weather event, the economics collapse. The materials are too scarce, the degradation is too fast, and the fire risk is too high. To double the duration of a lithium battery, you have to double the entire battery. You need twice as much cathode, twice as much anode, twice as much casing. It is linear scaling, and it is prohibitively expensive. This brings us to the concept of the flow battery. Flow batteries are the marathon runners of the grid. Unlike lithium, which stores energy in solid blocks, flow batteries store energy in liquid tanks. This separates power from energy. The hardware stack determines how fast you can discharge, but the tank size determines how long you can go. If you want to double the duration from 10 hours to 20 hours, you don't build a new battery, you just buy a bigger plastic tank and add more fluid. It is the cheapest theoretical way to store massive amounts of energy. The problem is finding the right fluid. The current leader is vanadium, but vanadium is expensive, price volatile, and hard to mine. We need a chemistry that is dirt cheap and abundant. That is why scientists have been obsessed with hydrogen and bromine. The H2 Bridge 2 battery is elegant. On one side, you have hydrogen gas, the most abundant element in the universe. On the other side, you have bromine, which we can extract from seawater or brine pools. The chemistry is incredibly fast. When you discharge the battery, hydrogen splits into protons and electrons. The protons cross a membrane, the electrons power your house, and on the other side, they meet bromine to form hydrobromic acid. It is reversible, it is fast, and it offers high power density. But there is a reason we are not all running our houses on bromine batteries yet. The reason is that bromine is a nightmare. This is the central conflict of our story. The bromine trap. When you charge the battery back up, you convert that safe hydrobromic acid back into hydrogen and elemental bromine. Elemental bromine is a dense, reddish-brown liquid that readily vaporizes into a choking gas. It is one of the most corrosive elements on the periodic table. It eats through steel. It dissolves plastic. It poisons humans. Even worse for the battery, it permeates the membrane. It crosses over to the hydrogen side and ruins the efficiency of the cell. For decades, this inability to safely cage the bromine killed the technology. But recently, that has changed. The breakthrough didn't come from better pumps or stronger steel. It came from supramolecular chemistry, the art of building traps for molecules. The first solution scientists developed was the use of bromine complexing agents, or BCAs. Imagine bromine as a hyperactive child that breaks everything in the room. The BCA is like a heavy backpack you strap onto that child. These are bulky organic molecules, usually ammonium salts. When the bromine forms, it immediately grabs onto the BCA to form a polybromide complex. This complex is a heavy, oily liquid that sinks to the bottom of the tank. It doesn't vaporize, and it doesn't cross the membrane easily. This made the battery safe, but it created a thick sludge that was hard to pump, slowing down the reaction. We needed something better. This is where we see the cutting edge of materials science, specifically from institutions like KAIST in South Korea and MIT. They moved beyond the backpack idea and started designing porous organic cages. These are individual molecules shaped like hollow polyhedrons. They are designed with windows exactly the right size to let a bromine molecule slip inside, but the chemical environment inside creates a strong attraction. It is a literal molecular jail. In recent studies, researchers synthesized nitrogen-rich cages that capture bromine vapor with terrifying efficiency. The bromine essentially hibernates inside the cage. This allows the battery to operate with almost zero free bromine vapor. It eliminates the corrosion risk and the safety hazard, while keeping the bromine chemically active enough to deliver high power. While the chemists were building cages, the architects at Rice University in Houston were revolutionizing the scaffold. A battery needs an electrode surface to host these reactions. It needs to be conductive, cheap, and porous. Under the leadership of Professor James Tour and Haoshan Wang, Rice University became the epicenter of a technique called flash Joule heating. They found a way to take ordinary materials, asphalt, plastic waste, even banana peels, and blast them with electricity to turn them into high-value porous graphene and carbon scaffolds in milliseconds. This provides the perfect surface for the bromine reaction. Even more interestingly, Rice's work on lithium extraction creates a symbiotic relationship. Bromine is often a byproduct of lithium mining from brine pools. The waste product of the lithium revolution is the fuel for the bromine revolution. So we solved the safety issue with cages and the hardware issue with flash Joule carbon. But the story gets even better. In 2024 and 2025, researchers at the Dalian Institute of Chemical Physics unveiled a 2-electron miracle. In a traditional bromine battery, for every bromine atom you use, you transfer 1 electron. It is a 1-to-1 ratio. But the researchers introduced specific amine compounds that act as both a trap and a participant. This unlocked a 2-electron transfer process. Instead of stopping at elemental bromine, the reaction proceeds further to form brominated amine compounds. This effectively doubles the capacity of the battery without increasing the tank size. It is like downloading a software update to your car and suddenly having a gas tank twice as big. This high-energy bromine trap also dropped the concentration of free bromine to near zero, meaning you could use cheaper plastic pipes and membranes without them melting away. So, scientifically, we have won. The trap works. But just as the technology matured, a new trap emerged. This one wasn't molecular. It was geopolitical. Bromine is abundant in the ocean, but extracting it from seawater is energy-intensive. The economic supply comes from high-concentration brine pools. The world's primary source is the Dead Sea, shared by Israel and Jordan. The second major source is the Smackover Formation in Arkansas, in the United States. In 2024 and 2025, as global tensions rose, the supply chain for critical minerals began to fracture. The reliability of shipments from the Middle East came into question. This leads us to a major pivot in the industry. Elestor, a Dutch company that was the undisputed commercial leader in hydrogen-bromine batteries, dropped a bombshell in 2025. After years of piloting successful bromine systems, they announced a pivot to hydrogen iron flow batteries. Their CEO was blunt. He cited geopolitical turbulence. The risk wasn't that the battery didn't work. It worked beautifully. The risk was that building a global grid storage infrastructure on a chemical sourced from a potential conflict zone was repeating the mistakes of the oil era. This creates a fascinating schism in the future of energy storage. On one side, you have the Iron Age. Companies like Elestor are moving to iron because it is everywhere. It is heavier and has lower voltage than bromine, but it is geopolitically boring. In grid security, boring is a feature. On the other side, you have the domestic bromine boom. In the United States, the bromine trap is becoming a gold rush. The Smackover Formation in Arkansas is already being tapped for lithium using those advanced filtration technologies we mentioned earlier. The bromine byproduct there is massive. For the US market, hydrogen-bromine remains a prime contender because the source is domestic and secure. This leaves us on the precipice of the long-duration energy storage era. The grid of the 2030s will require batteries that can discharge for 100 hours straight to survive a winter storm. Lithium cannot do this. Hydrogen-bromine and hydrogen iron can. Imagine a facility in the Texas Panhandle. It looks like a small chemical plant with rows of large tanks. When the West Texas wind howls at night and electricity prices turn negative, this plant sucks in gigawatts of power, splitting hydrobromic acid into hydrogen and trapping bromine in those porous organic cages. 3 days later, the wind dies. The sun is blocked by clouds. The grid is starving. The plant reverses flow. The hydrogen recombines with the trapped bromine. Gigawatts of power flow back into the grid, hour after hour, day after day. The bromine never leaves the loop. It is never consumed. It is a closed cycle of infinite rechargeability. The bromine trap is no longer a cage for a dangerous gas. It is a vault for sunlight and wind, holding them safe until we need them most. The science is done. Now the market must decide if it is brave enough to open the cage.